We're living in this absolutely wild time where AI can write poetry, it can generate these incredible images from nothing, and it can even write its own code. But there's one classic sci-fi promise that's still just a dream: the robot butler. So why is that? Let's get into it. Seriously, think about it. We have these powerful AIs that can ace the bar exam, but we still don't have a robot that can reliably fold our laundry or wash the dishes. It turns out the hardest problem for AI isn't thinking, it's doing. Physically acting in our messy, chaotic, and totally unpredictable world. And this all leads us to what you could call the robotics paradox. The digital brain is ready and willing, but the physical body, well, it's pretty much stuck on the factory floor. Just look at this contrast, it's staggering. Digital AI is just exploding, growing exponentially. It's general purpose, it's adaptable. Meanwhile, physical robotics is kind of plodding along. It's making slow, linear progress. Most robots are still these incredibly brittle machines that can only do one single task in a super controlled environment like a car factory. They're so fragile that a tiny speck of dust can literally shut down an entire production line. Adaptability? Pretty much zero. So what is the holdup? Why are physical robots lagging so far behind their digital cousins? Well, let's break down the massive roadblocks that have been holding this entire field back for decades. So according to robotics expert Sergey Levine, it really boils down to three core challenges. First, you've got the data problem. See, language models have the entire internet to learn from. Robots? There's no giant library of physical data for them. Second, the generalization problem. A robot that learns to load a dishwasher in your kitchen would be totally lost in mine. And finally, the robustness problem. The real world is just messy, and a tiny unexpected change, like, a toy on the floor, can cause a total system failure. But what if there was a way to tackle all three of these huge problems at once? Well, that is exactly what's starting to happen right now. It's all thanks to a totally new kind of AI model that's basically giving robots a new brain. The big breakthrough here is the shift from large language models to what are called vision language action models, or VLAs. Okay, the easiest way to think about this is like GPT, but for the physical world. Instead of taking in text and spitting out text, a VLA takes in video from its cameras, a command like fold the laundry, and then it outputs the exact physical actions the robot needs to perform. And here's the gist of how it works. It's a simple three-step process. First, perception. The model uses its cameras to see the world, and it uses a language encoder to understand what you just told it to do. Second, fusion. This is where it combines what it sees with what it heard, creating a single, unified understanding of the situation. And then, here's the magic. An action decoder translates that understanding into super precise physical movements. Now, to really see this in action, let's take a look at a cutting-edge VLA. It's called Pi-Zero, from a company called Physical Intelligence. Because, you see, the model itself is only half the story. The other, and maybe even more crucial half, is the recipe they use to train it. As Sergey Levine himself puts it, the recipe is everything. For language models, the recipe is pretty straightforward, right? You just scrape the entire internet. But for robots, no way, you can't do that. You need a much, much smarter approach. And here it is. The secret recipe for Pi-Zero is this two-stage process. First up is pre-training, and here it's all about quantity over quality. The model soaks up over 10,000 hours of diverse, messy, varied robot data. This builds a kind of common sense about the physical world. Then comes post-training, and here the script flips. It's quality over quantity. The model gets fine-tuned on just a few hours of really high-quality data to master a very specific task, like, say, folding a shirt perfectly. Now, here's the part that sounds a little weird, but it's absolutely critical. Using only perfect, good data is actually bad for training robots. Why? Because in the real world, robots are going to make mistakes all the time. That messy, low-quality data is so important because it doesn't just show the robot errors, it also shows the robot how to recover from those errors. That's how it learns to get back on track when things inevitably go wrong. So what's the actual payoff from this new brain and this new recipe? Okay, let's walk through Pi-Zero's famous laundry folding demo. It all starts with a pretty simple scene. You've got a robot arm and a basket just full of unfolded laundry. So the robot's vision system locks onto a single, crumpled t-shirt in that pile. It reaches in, it grabs it, pulls it out, and then it starts to just dexterously manipulate it, unfolding the fabric to lay it out flat on the table.
This is exactly the kind of high-dexterity skill it learned during that focused, quality over quantity post-training. But here is where it gets amazing. Watch what happens when a researcher just interrupts the whole process by throwing another shirt onto the table. The robot, using that common sense from its pre-training, it recognizes this unexpected object. It pauses its task, picks up the new shirt, drops it back in the basket, and then just seamlessly goes back to what it was doing. It's basically thinking, hey, I'm busy here, get this out of my way. And then the robot finishes the fold with these incredibly precise movements and places the shirt neatly onto a growing stack. I mean, this isn't some rigid pre-programmed routine. This is a general purpose model, adapting to a chaotic situation in real time. It's a huge deal. So, if robots are finally starting to learn, what does that actually mean for the future? Where does all of this go from here? So what is next? Well, researchers are already pushing robots to follow really complex and nuanced instructions. Things like clean the kitchen, but leave the plates on the table. The holy grail, though, is to generalize these skills to any object, in any home, on any kind of robot. This is the path to the true general-purpose helper robots that we've all been dreaming about. And all of this leaves us with a fascinating new question. For decades, the big challenge was how to teach a robot. But now that we're finally starting to figure that out, we have to decide, what should we teach them first? The age of the helpful robot is probably a lot closer than we think. The only question is, are we ready for it?